Hello everybody, welcome back to another episode of the problem solving series. Today's video we are going to be covering all things fluids. So I'm going to break this up into I think 3 different subtopics, since the topic of fluids and also the next video I'm talking about, which is going to be temperature, heat, and thermodynamics. Both of these are kind of general, broad topics that have a lot of, I like to think of them as kind of like these potpourri topics because they have a really large mix. And it's much more where I feel like the previous chapters are a little bit more about depth. These two are a little bit more about breadth. So there's a lot more to cover, but we don't go as deep with any of these concepts, I don't feel like. So first I'm going to go through just a couple general physics concepts and definitions of things. So first we have that pressure is force divided by area. So that's not just for fluids, that is for any force being applied over an area, it will give you a pressure. And then the other is going to be that density is defined as mass divided by volume. One thing I will kind of point out at the top is for fluids especially, we run into this issue of having variables, uppercase, lowercase, and then also Greek letters that all look very similar to one another. So mainly we have this capital P that we use for pressure, and then we have this lowercase Greek letter rho that we use for density. And if you're not careful with your handwriting or just differentiating between the two, you could run into large mistakes very quickly if you mix up a pressure and a density. So I just want to be kind of clear about that. And then capital P in this case is not the same as power, so we're reusing variables. But mainly the thing that I get nervous about with this section, especially with my own handwriting and how it comes off, is that we have capital V's for volume and lowercase v's for velocity. Now I do put text on the screen, so those will be up, of course, for writing the equations in my videos. In the voiceovers, when I go through the examples, typically what I try and do is I'll put like those little feet on my V's so that you know, for volume, so that you know that they're capitalized. So you might want to consider doing something similar for yourself, just to be able to differentiate between the uppercase V and the lowercase v, because again, then you will run into errors and make mistakes and do your calculations incorrectly if you switch up those quantities. With that being said, now, so those are the general definitions and concepts and equations that I wanted to present to you. Now we'll go into static fluids. So number one equation that we have for static fluids is that the pressure from a fluid is going to be equal to the density of that fluid times gravity and then times h. So this h is going to be the vertical distance that you are under the surface of that fluid. So it really should be, so technically it's a depth, it's not a height. But it's the depth below the surface, but typically a capital H is still used to denote that distance in that equation. And then something too that you, or I guess, I forget, I never remember all the names of these laws. I want to say, I think that this is Pascal's Principle. And this is applied for cases of hydraulics. So if you have a hydraulic press, a hydraulic lift, or anything where they're bringing in that term hydraulic, all that says is that if you have a fluid that is experiencing an external pressure, and typically this is also for a fluid that's like encapsulated in a volume. So a lot of the times the context that you see this in is in some sort of hydraulic machine, so the machine is filled with fluid, and if you have some external force exerting or providing an external pressure on that liquid, the pressure everywhere in the liquid is going to increase by that amount of external pressure. So there's going to be that external pressure is applied everywhere throughout the fluid. That is really helpful technologically, if you have something like a hydraulic press, that if you have a small area with a small force, but that still gives you a decent amount of pressure, if that same pressure is then applied over a larger area, you get a very large force out of it, and then you can lift something like, say, a car. I will be going through a full example of that in the voiceover portion of this video, so you'll get to see an example of how that gets used. Typically, they write that in the textbook sometimes as the pressure in is equal to the pressure out. I find that a little misleading because the caveat there is that those pressures are going to be at the same vertical height, so that they're kind of initial pressures before the external pressure is added, that they're going to be the same, and then the external pressure, if they're at the same height going in, will be the same coming out. So just kind of keep that in mind, that I like more so to think about it in terms of just kind of that sentence overview, that external pressure applied to a fluid is basically evenly applied throughout the fluid. So, that is that. Probably the most important thing that we're going to get from this fluids chapter, in my opinion, is going to be talking about the buoyant force. So when we have an object submerged in a fluid, there's going to be pressure on top if it's fully submerged, but that pressure is not going to be as much as the pressure felt on the bottom of that object, since the bottom is a little bit further down. So again, that pressure equals rho GH coming into play. And that pressure difference is going to provide a net upward force that we call the buoyant force. Conceptually, what can be handy is to think of the buoyant force as that it's the weight of the liquid being displaced by the object itself. So if an object is floating, that could mean that only part of the volume is submerged, or the total volume is submerged, depending on the density of that object. But we write the buoyant force as the density of the fluid times the volume submerged by the object times gravity, and that's equal to the amount of weight of the liquid that's being, or not liquid, but fluid being displaced by the object that's being placed in it. The three kind of situations that you can get from this with a problem is that you have a object that's partially submerged, you have a object that's fully submerged, but that the buoyant force is still balancing the object's weight so it doesn't sink. But if the weight of the object is greater than the buoyant force that can be provided by the liquid, so the maximum buoyant force that can be felt on an object is going to be the density of the fluid times the object's total volume times g. So if the weight of the object is greater than that buoyant force, then the object will sink. The trick that I see, or like the tricky thing with buoyancy problems and with fluid problems in general, is that because we have volume playing such a big role, we end up seeing things written in terms of densities, or we're interested in finding densities much more of the time than we are interested in finding masses. So it's very, very common, I feel like, to rewrite masses in terms of density times volume instead of just leaving them as mass, and then you get things canceling out. Again, I will show examples of this in the voiceover section of the video, but just to kind of give an overview and a sneak peek of what sorts of things that you can expect that make these questions a little bit less straightforward, and also just combine concepts as well. There's that for you. The other thing that I want to include with talking about buoyant force is that a lot of the times problems for buoyant force describe, like, they give you the weight of an object in air, and then they'll have it submerged in a liquid and give you the apparent weight, or ask you to solve for the apparent weight. So the apparent weight of a submerged object is going to be equal to its actual weight minus the buoyant force that it's feeling from the fluid that it's in. So I'm trying to keep it a little bit general because I have seen questions where technically then we don't know the actual weight of anything measured on Earth because we do have the pressure of air around us and we are sitting in a fluid. but it's so minuscule and we don't really think about it, so it doesn't really affect us too much. But I definitely have seen problems where it's like, well, this scale weight is technically the apparent weight with our buoyant force being air. If we can calculate the buoyant force of air, then what is the actual real weight of the object? Something like that. But yeah, ultimately, apparent weight is equal to actual weight minus buoyant force. That's really all that you need to know. The last subtopic that I'm going to discuss is going to be fluid dynamics. So we have two basic equations. I guess I'll mention a third kind of special case that could be optional depending on your professor. You might not see it, but I'll put it in here since I know that my students for this class that I'm in are going to see it. The first one is just the equation of continuity. It's basically a mass conservation idea. And all that says is that the volume flow rate, so the amount of volume moving for a fluid at any given time or over a change of time, needs to be constant. So if you have a pipe that has a larger area and then it condenses down to a smaller cross-sectional area, the speed should be increasing for that smaller area, or we say the area times the speed of the fluid is constant. Typically that's written as A1 V1 is equal to A2 V2. So again, we have our lowercase v's, and then all of that is equal to the change in volume over the change in time, which would be our uppercase V. So this is one of the ones, and it's these fluid dynamic equations that I get worried, and you just have to be a little bit more careful with keeping track of your variables so that you're not switching up volume and velocity, because that will be a big no-no. A special case for this volume flow rate is going to be for incompressible laminar flow through a cylindrical tube. So that's a lot of assumptions, but we could write that as pi r to the fourth pressure 1 minus pressure 2 over 8 times the viscosity, which is the Greek letter eta, times the length of the pipe that you're going through. Again, this is the one that's going to be a little bit more dependent on the class that you're taking, whether or not you'll see this equation. And again, this is very specific for moving through a cylindrical pipe, so nothing crazy shaped. Are you going to be able to use something like that? And the R in that is going to be the inner radius of the pipe, so that's kind of important just to keep in mind. And then the last equation, which I would say is arguably the second most important equation in fluids after buoyant force, is going to be Bernoulli's equation. This is essentially an energy conservation equation where every term has been divided by volume. When you do that, you get that pressure plus 1/2 density times velocity squared plus density times gravity times height is going to be constant. So again, we typically write that with subscripts of like P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. So that's a lot. I might have missed something, but I will have the equation here so you guys can see it and copy it down correctly. And probably the biggest thing I would have to say with this one is more so just knowing when you can set your velocities equal to 0, when you can set your y's equal to 0, and when you can set your pressures equal to atmospheric pressure. So a lot of the times I feel like this is applied to, well, the example that I'm going to go through will kind of touch on this a little bit, but if you have, say, like a large water tank that has a hose attached to it, I feel like that's a really common example. That's the one that I'm going to go through as well. Anytime you have the fluid kind of meeting the air, so at those openings where the fluid is in contact with the air, the pressure has to be the same and equal at those points. So the pressure in the fluid at the openings is equal to the atmospheric pressure. And that would be at both ends if you have, again, say a hose squirting water and then an open tank. The other major assumption that you can make within that situation and situations that are similar is that if the area of the tank is very, very large, we can assume that the velocity at that point is going to be very, very small. So that kind of stems from, again, that continuity equation that we talked about just before. But essentially, if that A becomes so big, but that delta V over delta T has to be constant, then that means the velocity of the fluid itself has to become pretty small. And in a lot of cases, you can usually assume that that's zero. It makes things really simple. And then for the Y's, knowing what to set equal to zero, that's just going to be very similar to doing gravitational potential energy, where you want to pick your 0 point to be, and then you just measure your heights, positive and negative, from wherever your 0 point is. Okay, so I think I've rambled enough. That is the explanation for all of fluids and all the equations. Oh, the only thing I think I forgot to mention is going to be the difference between absolute pressure and gauge pressure. So gauge pressure doesn't take into account the atmospheric pressure. So absolute pressure is equal to gauge pressure plus the atmospheric pressure, which typically we think of as 1 ATM being the unit, and then to put that in scientific, standard scientific units, so SI units, that would be 10.1. 1.01 times 10 to the 5 newtons per meter squared. Newtons per meter squared is also called a Pascal, and that's the scientific unit for pressure. Okay, now I think I've covered everything I need to. Let's jump into our voiceover portion where you can see all these equations in action and how to use them.
2/3 of an object is submerged in water. Density of water is 1,000 kilograms per meter cubed. What is the density of the object? Okay, so this is going to be an example using buoyant force. So we'll have volume submerged is 2/3 V total for this object. And then we will also probably should have done this first. Draw this object partially submerged, and we could draw the forces on it. So we'll have the mass of the object times gravity pointing down, and we'll have the buoyant force pointing upwards, and these two are going to be in balance with one another. So we can say that F buoyant force is equal to mg, and then we can substitute in that the buoyant force is the density of the liquid, or the density of the fluid that we're in, which is just water, times the volume submerged, times gravity equals the mass of the object times gravity. So we will be able to cancel out g's from either side here, but we have to do a little bit of a trick here because we have the submerged volume in terms of the total volume. And since we're interested in finding the density, we can actually write the mass in terms of the density and the volume of the object as well, and then we could get some things canceling out. So over on the other side of the diagram, we can write density is m over v total, which if we multiply both sides by that v total, we'll get mass by itself. So v total times density equals m. We'll substitute that in, and we'll also substitute in that 2/3 v total in for v sub. Then we can cancel out a v total from both sides, and we'll get that the 2/3 density of water is equal to the density of our object. So 2/3 times 1,000, which would be 667 kilograms per meter cubed. I'm going to go ahead and box that, and that will actually be useful information then for our next question. So now the object is going to be fully submerged in a container of another liquid. The apparent weight of the object is going to be half of its actual weight. What is the density of the new fluid? So we do have our density object that we just found, we know apparent weight is going to be half of the actual weight. And then when we draw our fully submerged object now, since we have an apparent weight, that means that our buoyant force is not going to exactly cancel out our weight, and the difference that we have between these two is going to be the apparent weight. So the apparent weight is going to be equal to mg minus the buoyant force, where apparent weight is 1/2 mg, so I'll make that substitution. And then I'll also substitute in for FB that's going to be density fluid. Since the total object is submerged, I'm just going to write that as V total, and then that is times G. I'm going to go ahead and cancel out a G from everything. And then I'm going to subtract an M from both sides to get a negative 1/2 M equals negative rho fluid times V total. Since we have a negative on both sides, we can cancel those out. And then the other thing I'm going to do is divide both sides by V total. Now, if we see that we have M over V total, we can rewrite that as the density of the object. So we'll end up with 1/2 density of the object equals density of the fluid. And 1/2 of 667 is 333.5. A sketch of a hydraulic press is shown below. Find the pressures and forces at the 3 points listed. So we do already have the first force, so I guess I'll just label that one since I didn't do it already. So the force being applied at spot 1 is going to be that 500 newtons, and our area is going to be 5 times 10 to the minus 5 meters squared. So we're just going to use that pressure is equal to force divided by area. I'm just going to include all 1 subscripts at that since we're looking at this first location. And we'll have 500 over 5 times 10 to the minus 5. And that's going to give me 10 to the 7 Newton per meter squared, or Pascals. You can also write that as PA. Now, because this inner chamber is all supposed to be filled with fluid, which I'll actually color blue to make that a little bit more clear, the pressure at point 1 is going to be equal to the pressure at point 2. So P1 is going to be equal to P2. So then we can say P2 is just going to be also equal to that 10 to the 7 Pascals. And we can get force 2 from P2 equals F2 over A2. And we multiply up the A2 to get the force by itself. So that area 2 times pressure 2 equals force 2. And our area is 5 times 10 to the minus 3 times 10 to the 7 will give us our force 2 being 5 times 10 to the 4th. And we'll box that. And then because of equal and opposite reactions, we're actually going to have the force on 3 being equal to the force on 2. So now the forces are going to be equal between spots 2 and 3 instead of the pressures. And let's see if I could fit that up here. So F3 is equal to F2, which is equal to our 5 times 10 to the 4. And then now we can use the force and the area to get the pressure. So P3, 5 times 10 to the 4 over 5 times 10 to the minus 4 will give us 1 times 10 to the 8 pascals. A large tank that is 5 meters high has a hose attached at the bottom of it with a tapered end. Find the pressures and velocities at all of the points listed on the figure below. If the hose is being used to fill a 100-liter pool, how long will it take to be filled? Should be added on there. Okay, so, and then I guess I'll also just kind of fill this up with blue, so that way we know that this is where all the water is. So first thing that we can say is that first I guess I'll mention the fact that since we're assuming that the area of the tank is going to be so much larger than the area of the hose, we can assume that the velocity at point 1 is going to be equal to 0. So this statement here, A1 is much, much bigger than A2 or A3, tells us that we can assume V1 is going to be equal to 0. Then, because the tank at point 1 and point 3 is open to the air, the pressure at both of those points is just going to be the atmospheric pressure. So P1 would be atmospheric pressure, which is 1 point, I'll round it, it'll just be 1 times 10 to the 5 Newton per meter squared. You can box those, and then I'll also put P3 is equal to P0, which again is just our atmospheric pressure of 10 to the 5 newtons per meter squared. Because we know the velocity, and actually I should have drawn the height on here as well, so this is going to be 5 meters. Since we know the velocity and the pressure at point 1, and we know the pressure at point 2, and we have the height between them, we can use Bernoullis equation to find V3. So we can use P1 plus 1/2 rho V1 squared plus not 1/2, plus rho G Y1 equals P3 plus 1/2 rho V3 squared plus rho G Y3. So we already know that our V1 is equal to 0. We can go ahead and also say our V3 is equal to 0. If we want to call our Y1 5, then our Y3 would be 0. And just to also simplify things, I'm going to substitute in that the P1, and I'll just plug the numbers in. So we'll have 10 to the 5 plus 1,000, 9.8 times 5 equals 10 to the 5 plus 1/2 1,000 V3 squared. If we subtract 10 to the 5, that'll cancel both of those out. And I'll go ahead and evaluate 1,000 times 9.8 times 5. So that'll be 49,000 equals 500 V3 cubed. We'll divide both sides by 500, and that gives me 98 is V3 squared. So we'll go ahead and take the square root of both sides, and that gives me V3 is 9.9 meters per second. Once we have that V3, I'm going to zoom out a little bit. Since we have A2 and A3, we can use the continuity equation to find what the velocity at point 2 is going to be. since we don't know the pressure there either, we can't jump right into doing Bernoulli's equation just yet, but we can use that V2 times A2 is V3 times A3. V2 is what we're solving for. A2 is 10 to the minus 4 equals 9.9 times 9 times 10 to the minus 3. Divide both sides by 10 to the minus 4. And I realized actually, so this should be, I meant to make this area 10 to the minus 5. So let me change that first before I plug it in my calculator. Okay, and this is going to give me V2 is 8.9 meters per second. So as we expect, the velocity should be a little bit less since our area is bigger. And then lastly, we could find P2 by using Bernoulli's equation. So P2 plus 1/2 rho V2 squared plus rho g y2 equals P3 1/2 rho V3 squared plus rho g y3. Now we know that y2 and y3, we called those heights 0, so I'm just going to put those zeros through there. And P2 plus 1/2 1,000 8.9 squared equals 10 to the 5th plus 1/2 1,000 9.9 squared. The right hand side is going to give me 149,005. The left side is going to give me 39,605. And then we'll go ahead and subtract that 39,605 to get 109,400 pascals. Now, I didn't ask this on here, but just in case, if I had wanted the gauge pressure instead, this is going to be our absolute pressure. So if I wanted to get gauge pressure from this, so I'll say PG2, that would be absolute pressure at 2 minus atmospheric pressure, so we'll just take that minus 10 to the 5, and gauge pressure would be 9,400.
All right, and there you have it. So that is my explanation of fluids. Of course, this is not going to be completely comprehensive, but I think that it gets the basics across and hits kind of the foundational fluid information that you need for a physics class. So thank you guys so much for watching. I hope that you enjoyed today's video. I will see you guys in the next one, and until then, happy physicsing!
Oh my goodness! All right, pretty boy.